we consider a point where fx equals fy equals 0. The surface is flat at this point. Had to stop there for a minute and get rid of a defective Sharpie. Okay, now, fx equals fy equals 0, surface is flat at this point. So as we move away from this point in the x direction or in the y direction, any change in the value of our function, which is flat at this point, is going to be driven by curvature. So a change in the f of x, y value, changes are driven by curvatures. We could also make the statement that our total differential, which is fx dx plus fy dy, is 0 at this point. Doesn't stay that way, but it's 0 at this point, so that changes in x and changes in y will cause changes in f only if fx and fy change. The curvatures that matter are the curvature in this direction, which would be the curvature fxx, curvature as we move in the x direction, curvature fyy as we move in this direction, and fxx and fyy are not actually curvatures. Just to get the notation straight, we'll say the curvature from fxx and the curvature from fyy, and a curvature out in this direction, which is going to be fxy. Now, the combined effect of the fxx and fyy curvatures is fxx times fyy. If fxx has the sign opposite fyy, that means that the curvature in this direction is different than the curvature in this direction, either that's curving down as we move in the x direction and up as we move in the y direction, or vice versa, up as we move in the x direction and down as we move in the y direction. So I'm going to say that if fxx and fyy have different signs, then we have no escaping. We have to have a saddle point. You can't have a positive and a negative curvature meeting at a point and not get a saddle point. And we'll note that if fxx and fyy have different signs, then fxx times fyy is negative, so that our discriminant, which is fxx fyy minus fxy squared, has a negative sign. That is, this is negative, fxy squared is positive, so when we subtract it, that makes our result even more negative. So it doesn't matter what fxy is. It doesn't matter what tendency the curvature in this direction has. If the curvature in this direction is opposite to the curvature in this direction, then you have a saddle point. I note that I labeled this curvature from fxx and from xy. I better do this fyy. We got a curvature from fxy, not a curvature fxy. Next, we'll examine the cases where fxx and fyy do have the same signs. The question then is, do those signs match the curvature of fxy or do they not? And if they don't, then which one wins?